All right, now we have all the tools that we need to solve systems of ODEs. And in particular, let's try to solve x prime equals ax, where A is the matrix 7 minus 3, 10 minus 4. And it turns out it all just boils down to finding all the eigenvalues and eigenvectors of A. So let's do that. So first, let's find the eigenvalues. So let's find Muhammad Ali. So determinant of A minus lambda I, which I like to remind you, you just subtract lambda from the diagonals. So 7 minus lambda minus 3, 10, and minus 4 minus lambda. And the determinant of A, B, C, D is AD minus BC. So 7 minus lambda times minus 4 minus lambda. And then minus 3 times 10. So remember those pesky negative signs. And that becomes minus 28 minus 7 lambda plus 4 lambda plus lambda squared, and then plus 30. So once again, beware of sign mistakes at this process. And this becomes lambda squared minus 3 lambda plus 2, which factors out as lambda minus 1 times lambda minus 2. And to find eigenvalues, you set this equal to 0, just like auxiliary equations. So the eigenvalues here are lambda equals 1 and lambda equals 2. Easy as 1, 2, 3. Now, let's find the eigenvectors. So first, let's do it for lambda equals 1. So here, remember, for every eigenvalue you find a null space. So in this case, we find a null space of A minus 1i. So what this means is you take the matrix A minus lambda I, which you find here, and you replace lambda with 1. So in this case, 7 minus 1, minus 3, 10, and minus 4 minus 1, minus 1. Like this. And then you put zeros because you're solving for the null space. So 0, 0. And then this becomes 6 minus 3, 10 minus 5, 0, 0. Let's simplify this. Let's simplify this a little bit. So here you can divide by 3. Here you can divide by 5. And you get 2 minus 1, 0. And then 2 minus 1, 0. And then now you can subtract one row from the other one. So subtract the first row from the second. And you find 2 minus 1, 0. And then 0, 0, 0. Which again is what you want. You want a row of zeros. And so this tells you that if we have the eigenvector xy, 2x minus y equals 0. So y equals 2x, dos x. And so eigenvector v, which is xy, is x 2x. And that becomes x times 1, 2. And so an eigenvector for lambda equals 1 is simply 1, 2. So remember this. And now let's move on. And let's do lambda equals 2. So here's step 3. Lambda equals 2. So same spiel. We'll do null space of A minus 2i. So once again, notice how it's the same thing as our previous exercise of finding eigenvalues and eigenvectors. So 7 minus 2, and then minus 3, 10, and minus 4 minus 2, and then 0, 0. You simplify this to get 5 minus 3 and 10 minus 6. 5 minus 3, 0. And then 10 minus 6, 0. And then if you want, you can divide the second row by 2. And you get 5 minus 3, 0. 5 minus 3, 0. And once again, you can subtract one row from the other. And you get 5 minus 3, 0. And then 0, 0, 0. Or another thing you can do to make this a bit faster, you can subtract 2 times the first row from the second and also get 5 minus 3, 0, 0, 0, 0. Okay, and in this case, this tells you that 5x minus 3y equals 0. You can either solve for y in terms of x or do the guessing game as in the eigenvalue, eigenvector lesson. So for instance, x equals 3 and y equals 5 works. Why? Because 5 times 3 minus 3 times 5 is indeed 0. And so an eigenvector in this case is 3, 5. Last but not least, to find the solution is just an extra step. So step 4, solution. So what did we find so far? We find 2 eigenvalues. Okay. So we found an eigenvalue 1 with eigenvector 1, 2, and an eigenvalue 2 with eigenvector 3, 5. And in the next video, I will explain why this works. But here, just a little motivation. Because if you remember back in second order ODEs, we have y, let's say y double prime minus 5y prime plus 6y. We found the auxiliary equation, r squared minus 5r plus 6 equals 0, which gives you r equals 2 and r equals 3. And we found our general solution. So I won't use a and b as constants, but c1 and c2, because we already have a for the matrix. And you found that the general solution is c1 e to the first root t plus c2 e to the second root t. That's what we did for roots of auxiliary equations. It turns out it's the same thing here for the eigenvalues. So the general solution here, x of t, is now the following. So solution. So x of t, still a constant. So c1 e to the first eigenvalue t times the first eigenvector, because we want a vector. So x of t is a vector, plus c2 e to the eigenvalue t times the second eigenvector. So you see here, every eigenvalue goes with the corresponding eigenvector. And that's how you build your solution. So once again, once you found the eigenvalue and eigenvector, what do you do? Constant e to the first eigenvalue t times eigenvector. Eigenvalue and then vector. Plus C2 e to the second eigenvalue t times the eigenvector. Or once again, C1 and C2 are arbitrary. And in the next video, I will explain why this works.